Okay, thank you, Dave. Can you hear me? Yes. Okay, fine. I'm going to talk about drunkard's walks and their relation to the web. What I normally do is this, my work with the World Wide Web Foundation in Africa. For example, we work on citizen journalism with radio stations. Last year I had a talk about that. Next year I will talk about that. This year I talk about something different. When we travel around in Mali and Burkina and Ghana, we sit during our field trips, we sit for hours in the bus, and then you have time to think about things. And actually part of the work I'm going to present now, I did in the bus in Mali. And it's very bumpy, that's why you can understand it's about drunkard's walks. It has some mathematics in it. I try to keep that minimal and give you more the conceptual flavor. But I have been interested in the dynamics of the web, the evolution of the web in terms of link creation and link destruction, and node creation and node destruction. Generally, also the web is governed by power laws, and I will give an example. And I'm interested under what general conditions will power laws emerge in the web. I will give away the take-home messages already. What I will show is that clearly web users, and certainly you web scientists, are very independent and rational individuals, but still the web as a whole is behaving like a drunkard. Probably in all your web science curricula, you will have some stuff on power laws and what is widely known as preferential attachment. What I going to do secondly is put up some big question marks about preferential attachment, so that it will be clear that it is dubious that preferential attachment actually is governing the web as a first principle. And I use drunkard's walks as a method to show that. First, a recap on power laws. Power laws, you see that in blue. The probability that a node, say a web page, has k links is inversely proportional to the number of links, to a certain power, here alpha, and empirically this power law exponent is typically somewhere between 2 and 3, and that also holds for the web. There have been a number of empirical studies, and I give them over there a few examples. If you take a log-log plot, then you see a more or less a straight line. That's indicative of a power distribution. And also for the web, typically slightly above 2 is a number that you will often find. Power laws are counterintuitive in many different ways because of their statistics, because of the fact that outlier or extreme events are much more likely to happen than people tend to think. It's also known, if you have economic networks, as a rich get richer effect. So a big question in network science has been how to explain power laws. This is also a question for the web. This is the traditional way of doing it. Before I come to my approach to it, I will explain how it usually is done. You have a whole family of network formation models due to Derek de Solla Price, who was the first one to develop a network model for citation networks. And later on, a very similar model was developed by Barabasi and colleagues They coined the term preferential attachment. And the idea is conceptually quite simple. You take a node, you start with a node. This node is making some links and has a probability of making links. Then you stop, you add a new node. The previous one is frozen. The second node is doing its stuff. Then it stops, and so on and so on. And then if you take the limit of a very large network, then you will get the equilibrium situation. And then the idea is you have an equation like that. S plus 1 is the number of nodes you have, so it's the number of discrete events. And that is equal to what you already had, plus the changes that are made due to link creation. This is the original model by Barabasi and Albert. The lambda plus rates are actually the probability per event to create an additional link. It's handy for those who like mathematics to write it down in matrix notation, and then you see a few interesting things. To predict the situation at the next time point, you only have to know the previous time point, so there is no memory in the system. That is called the Markovian stochastic model. That simplifies things very much if there is no memory. And another key thing is that the right-hand side depends explicitly on discrete time. And that is mathematically not so nice a feature because it makes the model very complicated. And that is called that the transitions are non-stationary because they depend explicitly on time. So I want to do things differently because what is unnatural about this model is that you have to introduce nodes one by one, and then something happens with that node. That is unnatural for the web, where all kinds of things are going on all the time. New web pages come up, web pages get destroyed or taken out, links are created, links are destroyed, and these are different stochastic processes that happen in parallel, in competition, and at the same time continually. So I have been looking for a model that does not have this bias of one by one node introduction and freezing the nodes after they have done their work, but that everything should be able to happen all the time. And actually, that is a random walk, gives the possibilities to describe this correctly. What is a random walk? You have a drunkard, and this drunkard has the possibility to make a step forward, a certain probability. In our case, that's link creation. The drunkard also has a possibility to go a step back, which is link destruction. In this special case, there are potholes in the road, which is equivalent to the process of node destruction. And then finally, you have node addition, new web pages being constructed, and that is equivalent. You see the saloon over there, and basically the bartender has closed the saloon, but he is still kicking out the final customers one by one to get on their way to home. If you model this mathematically in continuous time, because that is another thing, we measure things in continuous time, not in terms of discrete events, then you get a continuous time random walk, and basically that's described here. If you also write it down in matrix notation, you see that it has a nice feature that it is stationary. There is no explicit time dependence on the right-hand side, in contrast to the Barabasi model. It has a feed-in rate, something you see often also in control systems, which is the node introduction rate. Okay, now we use this random walk continuous model to find out whether under what general conditions power laws occur. Recall what you do in the Price-Barabasi family of models is you assume something for the link creation rates and the link destruction rates. Preferential attachment is basically assume that the link creation rate, what is the lambda plus in my model, is simply linear. Then you calculate the stationary solution, the Q, and you can look at the behavior for very high K, so a high number of links, and then you can find out with a lot of mathematics that it indeed behaves like a power law. I do it the other way around because I'm interested not in specific models, but in the general conditions. So what I do is I use the principle of detailed balance, and that is basically if you have a steady state, then probability is flowing from here to here because of link creation, and from here to here because of link destruction. So imagine a Cirque du Soleil ring of fire. Lions are jumping from here to here and from here to here. If you want to keep the same number of lions all the time in these boxes, then that is basically what is called detail balance. And you can write that down very easily in the equation above. Then I say, I actually know what I'm looking for. The stationary solution should be a power law. And I fill that in. And then I get a set of what I call litmus test criteria for whether or not power laws occur. And this is a very, you can look at different possible cases, and I show here two of them. The first one is that you have link creation and link destruction as the dominant process. And then what you see is that the link creation rate is level k minus 1 divided by the link destruction rate at level k has this very simple 1 minus alpha over k behavior. And already qualitatively you can read a lot of it in it. It means that the functional structure as a function of the number of links for both the link creation and the link destruction rates must be similar. So you must have a similar functional structure. What is quite typical in natural systems is that you have a different functional structure, and that leads to the well-known bell-shaped kind of distributions. And also, the next order in 1 over k determines the power exponent alpha. So for example, if you would take in this special case that lambda plus and lambda minus are linear, then you have k minus 1 over k, which is equal to 1 minus 1 over k. So in the linear case, this special model says that alpha equals to 1. So you have Zipf's law, basically. If you make it quadratic, alpha is 2. I have another case, which is actually the original Barabasi model, because I can mimic that with my continuous time model. And you see that you have a very similar structure for the litmus test. What is different in the Barabasi model is that you ignore link destruction, which is artificial but fits citation networks, but not the web. And it assumes that there's a very high rate of node introduction. And then you also can calculate, for example, you can already see here, if you take preferential attachment which is linear. You have k minus 1 over k plus 1, which is roughly 1 minus 2 over k. So the typical Barabasi model will have power law exponents of the order of 2, but you ignore link destruction. You can make a whole mathematical analysis, and I have done so, also for other cases. And here are, let's say, the qualitative conclusions of this analysis. First of all, you can see that power laws can be explained by simple random walks. So, for example, I'm able to reproduce all existing literature results that have been done by means of the Price-Barabasi family of models. It also, because you have simple random walks, you have a dynamic model that in terms of realistic character is closer to what the web is doing than the one-by-one node introduction model. And that is unnatural, but it is also not needed. What you also can see is that linear preferential attachment actually requires growth of the network. Otherwise, it's not correct. If you take out growth of the network, the Barabasi models will have wrong values of alpha. And that is, many models in network science actually assume growth of the network. But what you can see with my model is that power laws also can emerge if you don't have growth. And actually, the first example I showed is an example of that. Secondly, because I'm interested in the general conditions, you can see that it's not only linear rates that can give you a power law, but also quadratic rates, or basically any polynomial, can give you power laws. So I have produced or generated a whole class of new network formation models that are a possible hypothesis. I cannot say that they are right, but the possibility of network formation models with nonlinear rates is really vast. And in the general case, you can show that actually, in order to reproduce the empirical values of the power law exponent alpha, link updates must be nonlinear. I think that's an interesting conclusion. Finally, a difference between my model is that it is in continuous time, and the traditional models are all in discrete time, but there is an important effect and difference when you move from discrete time to continuous time, because you have to set the time scale. The time scale is basically the mean time between events. And the transition rates, link creation and link destruction, are not only driven by the probability function structure, such as preferential attachment, but they factorize into a part that is the probability function and a part that is basically setting the mean time between events. And now, the mean time between events is most likely to differ depending on the number of links you have. Websites with a lot of links probably attract more traffic, so the rate of events is much faster than websites that do not have many links. So amount of traffic really directly influences the power law exponent alpha as well. And if you combine that, the probability function structure plus the amount of traffic, and you would, for example, both assume to be linear, then you would get the power law exponent equal to 2, roughly. So this is so far for the math. I have been thinking a little bit, because this is a statistical model, what kind of statistics would underlie such a model? and why that would occur. If you recall the famous random graph theory of Erdős and Rényi, there you form a network by adding nodes, and the statistical rule is all nodes that you select are equally probable. And then you can prove that you get these nice bell shapes, so no power loss. That's basically the trigger of developing new models such as Bassi and colleagues did. Now I can see from my model that is an alternative, which I call scale-free network statistics. If you don't say that all nodes are equally probable, but if you say all nodes plus existing links are equally probable, then that is sufficient to generate power laws in networks. So any object in the network that you select is equally probable. So basically, all paths to nodes, whether they are direct or indirect via a link, are equally probable. And if you assume that kind of statistics, then you automatically get power laws. And this gives an alternative causal explanation. There are different explanations put forward for power laws. One of them is called preferential attachment. There the idea is that apparently people have a preference to link to nodes that are richer. So you might see that as a kind of follow the leader mechanism. That's basically the idea by Barabasi and colleagues. John Kleinberg, who gave a talk here, developed a different model. He has developed a model called link copying. And there the idea is there is a certain probability that you select a node, but another probability that you select a link, and then you copy the link. It's a way of self-reproduction of the network. So that's kind of follow the herd principle. And it leads to the same mathematics as the preferential attachment, but the mechanism is different. My scale-free network statistics that all paths are equally probable is yet another assumption, because I do not have to say anything about individual or microscopic behavior. If I assume that people are independent and their preferences and behavior scatter widely, and you average over the adjacency matrix, then you can show that scale-free network statistics that on average and on aggregate, all links and nodes are equally probable. That is something you get. Then the question is why this would occur. And my answer to that, and that's a kind of, it is not mathematical, but that's conceptual interpretation. Scale-free network statistics occurs because we have information feedback. Basically, because of surfing and searching, network actors have a pretty good idea of all the nodes and all the links of a network. You can find them out, which is something you cannot do typically in natural systems. Radioactive decay has no clue what a network is. So the information feedback leads to actor knowledge about the structure of the network. That leads to scale-free network statistics that on average, every object, link, or node is equally probable, and that in turn produces power law. So this is a purely statistical effect. That would be my explanation, and you can avoid any microscopic or assumption on individuals. So your preferences can be whatever they are. I don't say that you prefer to attach to rich nodes. You can do what you want. Still, you can get power laws. That's it, basically. Thank you.